we are understanding remote sensing, and we were understanding capturing of images. If you are aware that in first 1-2 lectures, we understood about remote sensing, that how this technology enabling us to capture large scale data. And then after we understood how this captured data, its quality is getting affected. So we understood various resolutions, maybe like spatial resolution, then temporal resolution, radiometric resolution, and spectral resolution. And we also understood how microwave remote sensing enabling us to capture or store good quality data because of high reflectance, high transmittance. So that was the thing we were understanding. Now I assume that you have understood about capturing of the data. Now, after capturing the data on sensor, what we have to do, what we are supposed to understand, that what happens to data. Data means the remote sensing image. We have been understanding the remote sensing images in GIS as raster images. If you remember my lecture on GIS, we are understanding raster data model. Then in that we understood that how the raster grid and cell and quantity in this cell could be understood and could be utilized for analysis and finally for decision making. Likewise, here in remote sensing, before these data really taken to GIS, not all the data are taken to GIS. GIS we fetch, we take the data into GIS structure, GIS application only if it is required in GIS application. If that is not required, then this remote sensing data is having other standalone n number of applications. Like if you want a say land use map, then it is not necessarily that map to be created in geographic information system. This map can be created just by analyzing and processing the remote sensing data captured by the sensor. So what we are now doing, that what has been captured by the sensors, we now make sense, because sensors capture the reflectance of the various objects on the Earth surface. Now that reflectance captured on here is having a value in terms of percentage or in terms of intensity. So that it need to be converted into some meaningful information. The data need to be converted into some meaningful information. So we could understand this is an image, not a kind of data, figures, numerals. So those numerals are of no use to a layman when we look at remote sensing image. Second, remote sensing image is a digital image. It's not a like the photograph which you could hold. So we have to open it in the laptop or in mobile or in any other visualizing device. So what is this? That to open that, we are not interested in numerals and intensity values and percentage values, but we are interested in the map of the area. So how to create that map? For that, there are three major processes. That first is to display the image. Second, to apply certain corrections, because while capturing, all the information are not captured correctly. It does have a different distorted values. It does have many other distortions on the image, and we need to remove the distortion. Remove the distortion, and that distortion will be removed in the second part. First, we are understanding how to display the image as we could understand. not as the reflectance value or any other numeric value, but in terms of a more understandable view of this image. Then the last is that we need to do a better classification of all the information captured on the image. So today what we are understanding, we are starting with the first, that how to display the images, how to display the remote sensing data, data structure or image. Here is the way we are supposed to deal the data. This image data on disk. Image data on disk means your image. Image data on disk means on computer or laptop or on a removable hard drive or like those things. So any image on the disk is subjected to 3 guns, that is RGB. So this is image display system. What it is, like it is a monitor of your screen. Different color appears on the screen because of this RGB combination. All the colors are created because of these 3 basic colors, RGB, red, green and blue. So all the data are subjected. Gun is a name given because we are feeding the data into red, we are feeding the data into green, and we are feeding this data. All the data means this reflectance and the stored intensities here will be taken through this algorithm: red gun, green gun and blue gun. So when we subject all these data, then we receive the output here onto the other side. Output here onto the other side would be our display image, not the digital values or numerals, but we'll get a image here onto the other side. So what would be that like? I show you. What is the concept of RGB? That in order to generate a color display of a satellite image on the monitor, we need to choose data to be represented in red, data to be represented in green, and data to be represented in blue. Such a display is known as color composite. All the time in university examination, there are questions on false and true color composites, that how the image could be displayed in terms of a false color composite or in terms of a true color composite. So here what we are looking at, that which data is going into red gun, which data is going into green gun and which data is going into blue gun. So depending upon the data which are being subjected to red, green and blue, the color composite would be assigned. So you could say when we give colors or a combination, then 2 types of composites are created. First is false color composite. For FCC, the better known in short acronym form FCC. So it's a false color composite. When a false color composite created or formed, when the near infrared wavelength is subjected to red color gun, when the red wavelength is subjected to green color, red is not being subjected to red gun and green is subjected to blue. So all 3 are not having their natural colors. This near infrared, this is not a visible. This red color is visible range. So what is false color is formed when the data assigned to red, green and blue color, which are there, blue guns, red, green and blue guns on the display, is collected outside the visible range. Are collected means collected, captured by the sensor outside of visible range or outside of that band. Like here, this is red wavelength and it is being subjected to green color. So this green color band is not, this green color gun is not being subjected to green band, and this blue color gun is not being subjected to green band. blue band, and it is subjected to green. So whatever we get out of this this analysis algorithm or in software would be a false color composite. False color composite means your greenery, like vegetation on Earth's surface, may not appear green. Like your roads may not appear black. Your water may not appear like water. It may be dark or like any other color. So depending upon the input data, what is input data? We capture the remote sensing data in different bands. I have given you this all that we capture in visible range. In visible, there are different bands. And we capture them in infrared, far infrared. We capture also thermal range. Then we capture the microwave remote sensing. In the SAR, we have laser also. So these wavelength bands are used, and when these bands are not red, green and blue, then these are different color and need we are subjecting to different guns or different algorithm. You could say these are algorithms. These are programs in the remote sensing software. So red color gun means red color algorithm. Green color gun means green color algorithm for that. If we fuse the similar data, will get the true color composite. So I show you this example of false color composite. Now you look at this remote sensing image, which was taken by the satellite, and this satellite image represents that there are trees here, trees and other vegetation over here, but the color of this vegetation is red in this image. But this is not a kind of image. In image, when it is being captured by the sensors and stored, then all the grid and grid cells are having numerical values. Your image won't be like this. This is after being subjected to 3 guns, RGB, or 3 algorithms, you can say RGB, that this kind of FCC is formed, and these all vegetation are appearing red, not green. They should be green. So you could say this is not a true color composite. The composition of color is not true. It is a false. So that is what is need to be understood here. I show you the next natural color composite NCC or true color composite TCC. This is, you could give name to this composite, that natural color composite or true color composite is formed when the data assigned to red, green, blue algorithm is collected in the same wavelength. So those wavelength, if we collect data only in those RGB and we subject the algorithm, red color gun algorithm, green color gun algorithm, blue color gun algorithm, then what we get image as an output would be the natural color composite NCC or TCC, true color composite. So this is very important thing. Now you look the same image when subjected. These data are different, but area is same. The area is same. Here data which were subjected to RGB were into that band only. So what we are getting here, the green vegetation, the color of vegetation is green. The roads are appearing black. In the false color composite, there were roads, but still they are black. So that depends upon the combination of colors, because the formation of colors is depend upon the combination of RGB. So this is a natural NCC, natural color composite. Now, apart from this display, we have seen 2 displays of the images. One is the false color FCC and second is the true color composite or NCC, natural color composite. Now your images could also be black and white. We have seen that panchromatic cameras or sensors are there onto the satellite. So likewise, there are many other sources from where we get or receive the black and white images. A black and white image is one that has no color, but only white and black and shades of gray. The smallest value of the pixel is 0, that represent black. Black means any pixel or any cell of the grid is having, if value 0 means the color is black, and the largest would be 2 raised to the power L minus 1. L is the size of grid. minus 1 and that the highest number, the largest number would be white. If the value of L is 8, in that case, what will happen? The largest cell value would be 255. So these 0 and 255 is stored where? In the grid cell. In the grid cell, depending upon the intensity of reflectance. If reflectance is less 0, if larger reflectance, higher intensity values are being captured, then the value could reach up to 255 if L is 8. So in that case, we will get all the values from 0, 1, 2, 3 and up to 255. 0 would have a pure black color and 255 would have a perfect white color and in between shades of gray. Like this. So this represents zero value in the cell of the image. This represents 255. So this is how it appears the image. Now grayscale images you could find where? When we use a single band, we are not having, let's say, RGB 3 band to feed exactly those wavelengths where we find the RGB. So what if an image of a single band of multispectral image, out of a multispectral image we are feeding only single band into RGB, then what will get output as this black and white or grayscale image. If we are capturing remote sensing images through SAR, this is SAR images means what? Microwave remote sensing. So here image would be again grayscale. We do not get here because these are high resolution. If we go for more colors, then the total storage will go very large and it's difficult to process those images. So they are kept like this. An image from panchromatic sensors. So many sensors located on the different satellites on Indian satellites or like foreign satellites, they have, because of many other purposes, the panchromatic sensors. They out of say a set of 4 sensors, 2 or 1 is panchromatic. They capture information purposefully onto the satellite. So how it happens on the screen? Very critical statement you read: when red, green and blue display guns are fed the same signal, the resulting display on the screen will be black and white. The same signal, they are not being subjected to. All 3 guns or algorithms are different signals. Signal means the input image in terms of reflectance or intensity. This is black of the same image created with single band data. Single band data has been fed into 3 guns, 3 algorithms. What we get as output is this image. So this is how it appears. Now, as I said, that different as we display them with RGB or panchromatic, then what happens? That it requires lot of space and data need to be structured, means systematic, and need to be stored systematically. So all the multi-band data or single band data or say panchromatic data, we have a certain way of storing in remote sensing. This is just 2-3 types of storage system mentioned here. One is BIL, second is BSQ, and third is BIP. There could be few more here, but 3 are mentioned which are more popular. That common data structure, or you could say systems through which we store the data. The data is stored, you will say me that there is a grid and each cell would be storing the data, but machine language does not store it like that. As I explained you in the vector and raster, that the flat files in the machine language are different, and where there is machine storage, then it is like band interleaved by line. Band means the band in which we are conducting remote sensing, interleaved by line, then band sequentially, and this is band interleaved by pixel. So let's see the example of this. How? So this is band interleaved by a line. How? we have, suppose in a grid, m rows, n columns, and we have k number of bands. The data has been captured on the satellite in say 5 bands. K means 5 or 7 bands. It's a multispectral remote sensing. So a remote sensing image having m rows, n columns. So here, first what we do, we store the first row of each image, and we change the band 1 to K. Then we take the second row and then we change the band. So band interleaved by line, or you could say row. So this is rows. First we are going and changing the band. The second is sequential. Band sequential means band completely be askew. We won't change the band. Band 1 data, the data captured in band 1 would be stored, all the data, and then row 1 to M. So this is one image, complete image, band 1. So this is band 2, whatever has been captured would be shown here in band 2, and likewise. So in previous we are keeping row constant initially and changing the band and storing the data. Here in BSQ we are storing a single band first. We are taking the second band and third band and up to the kth band and so on. Now, if these images are being stored, then we need to have a kind of information in our mind that how much storage it would take onto our hardware, because one of the important factor in remote sensing and GIS is also hardware, requirement of hardware. So when we are working, say in the computational laboratory of civil engineering, then do we have that much storage where we could process the remote sensing images or not? So that is a big question. Do we have that kind of RAM that would process the images? So look at this. Assume that we are doing a remote sensing of area 10 km by 10 km. Say Ahmedabad is 25 km by 25 km. You can assume this safely as Rajkot or a smaller city like Bhavnagar. So that 10 km by 10 km is that much area. Now suppose we are doing remote sensing, capturing the images by sport satellite. These satellite may be Indian or may not be Indian, but it is having, we want to do this much of surveying or information collection of 10 by 10 km. Now, if we are using this satellite, then pixel size is 10 meter by 10 meter. That resolution, list 3, we are having 23. In sport, we are having 20 meter by 20 meter. So with this much resolution, how many images are going to be there in this? 500. If you divide this 10,000 meter divided by 20 meter, how many would you get? 500. So 500 by 500, and suppose sport is collecting data in 3 bands. Then we have to multiply that. This data would be 3 times, and each cell is having just 1 byte of information. So into 1. So total bytes are becoming like 7 lakhs or 750,000 bytes or 750 KB. So this is how we are coming up to the storage. So this is very nominal. Any computer can hold this much of data. Now we are going the same area being done with the remote sensing, but using a different satellite, say Iconos images. This satellite images we are examining. Then what will happen that here each cell is having 2 bytes and its resolution of Iconos images is 4 meter. So here we are having 20 meter resolution. Here we are having 4 meter resolution, and data also here collected in 4 bands. There it was 3 bands. So how this 10,000 here, 10,000 is requirement divided by 4. Here it was in the first it was divided by 20. Here we are dividing it by 4 into 4 bands into 2. The number of bytes being used by a cell. So we are multiplying twice. And if we do the calculation, we'll get 50 MB instead of 750 KB. Similarly, if we are going for SAR, that is synthetic aperture radar. Last time I have explained this SAR and SLAR data, how microwave remote sensing capture. So they capture panchromatic data, grayscale data, but their resolution is, look at 1 meter. They collect it in single band, and there are 2 bytes. There are 2 bytes per cell. So 10,000 by 10,000. Here we have divided by 4, but here since resolution is very high, it becomes 10,000 into 10,000 into 2 bytes per cell into 1 band. So how much it is coming out? 200 MB of data. Here it is a colored image. Here it is a panchromatic image, though 200 MB of data. So to open this file, we require say advanced or up-to-date softwares and also hardwares. So this is just explanation that there are a lot of data, and this I have given only one area, say 10 kilometer by 10 kilometer. ISRO and other agency, they are handling whole of the India. Not only 10 by 10 kilometer of city of Rajkot, but Rajkot district and all the districts of Gujarat and all the states of India. They are handling that much of data. So you could just imagine the requirement of hardware, why they are looking for up-to-date hardware to deal the remote sensing image. So this particular one slide would give you that insight into the data requirement, the enormous size, storage size they need. This is some of the, because of the data, the high resolution. This is the list, the initial first in the 80s, what we launched, list 3 sensors on IRS satellite 1C, list 3 sensor and captured. We are not in position to detect where the houses are. So this is only red, and this black. So you could imagine this appears a FCC, and things are not clear. I'm going with high resolution. This is higher resolution. What is this? IRS P6 list 4. Earlier was list 3 1C satellite. Here this is P6 IRS P6, and the sensor is list 4 LISS 4 image. Here the things are more clearer and they are visible. Roads are clearer, and you could look at more things. If we go for say Iconos, where the 4 meter is the resolution, so you could look at the buildings. You could make it out easily that these are buildings, different buildings, and these are open grounds. And this is IIT campus, and viewed using ADAS Viewfinder 2.1, a free viewer. So you could also try these images in your laptop if possible. This is far better. This is 1 meter resolution. The quick bird or SAR images, as I mentioned, this is less than 1 meter resolution. So each and everything you could find out where and how things are there. This is not a photograph. This is image, and this image represents say something like 2-3 kilometer by 2-3 kilometer here, just in one single exposure. Evolution of image analysis techniques. Till now, I have explained you how to display the images. Earlier, we understood capturing of the images and then display of the images. Now we are switching over to the analysis part. Then we'll switch over to the classification of the images. Okay, so this is a transition, one step, and then on to the next step. So the next step is analyzing the images. After displaying them, we need to analyze. So there are basically 3 major types of analysis. 3 major types of analysis, and depending upon the time period, in earlier times, like in 80s and 90s, pixel-based classification using spectral features. That spectral features, different bands we used, and we classified, analyzed the data. Now later on, as the resolution increased, enhanced, or better resolution, we are working with different, not only the spectral resolution, also the the radiometric. So look at this textural feature. Pixel, this is also pixel based and this is also pixel based. Whatever is there in the pixel or cell of the grid. So this is pixel based classification using spectral features, spectral reflectance, and here pixel based classification using spectral and textural features. So here these sensors are capable of recognizing, differentiating the different objects on the surface through spectral as well as textural features. The third, which are like object-based classification. Here this was pixel-based classification on the image. Now we are doing the object-based classification using spatial features, spectral and textural feature using high resolution images. Like every cell of the grid is having values, definitely yes, but when we locate certain things, when we display certain things, that this is the object or particular object onto the image. So we identify those objects and we do the classification that these are the trees and we classify them as trees. So classification based object based classification, we'll see in classification they are called like supervised classification and unsupervised classification, and we'll do that classification that is part of your syllabus and we'll understand. These are not difficult if you digest them, the terminology, different terminology. So there are pixel based and object based. Object based means we are looking at the object onto the surface and then doing the classification. And here we are least interested what is onto the Earth surface in first two, but we are analyzing whatever information has been captured by the sensor in the cell or in the pixel of the image. So that is what is the difference among these three. So you should be very quick to understand that presently with the high resolution data, we mostly conduct this object based classification. I'm not going to do this histogram concept in the theory part of it. I'll show you the image, the histogram image. This is a histogram of an image. And this is helpful in the analysis and easy to understand. Histogram is nothing, but it is like a bar chart. When you draw a graph, you do a bar chart kind of thing in your 10th or 12th standard, that preparation of bar chart. So where in bar chart we compare different variables. Say variable 1 is having this much of intensity and variable 2 is having this much of intensity. Here the same variable is having the different intensity. This is the variation. So in the histogram we say represent the variation or distribution of an feature or an a characteristic. So here suppose this is intensity and these are the colors of gray from 0 to 255 here, and in the different we are getting here the intensity here. So this is here well distributed among all. So this is white here color, this is black color, and different intensities, and they are well distributed. I'm going to next to show you where this histogram is used. Dynamic range of display system. Dynamic range of display system. Where is the dynamic range? This is dynamic range of the distribution. This is dynamic. It's not constant, not fixed. It changes. Dynamic range of display system, minimum to maximum range of intensities that can be displayed. Normal range 0 to 255 for grayscale, for color 0 to 255 for red, green and blue. If last statement is important in understanding the histogram, if minimum maximum range of data is comparable to dynamic range of the display device, good quality display is possible. This is the hardware. If minimum maximum range of the data is comparable to dynamic range of display device dynamic range, if it is comparable with, then the resolution or the display would be more clearer compared to if we have image having a histogram like this. Here the distribution of intensity is not there, but a peak value is there. You look at the intensity of the histogram is 15,000 something, but earlier it was just 8,000. Now this much change, but here distribution is not there. Here we do not have any values. Here we do not have any values. So it is not distributed well, and this is locally having a kind of intensity here, high intensity here. So this histogram means not suitable for better quality images or image analysis. That is what is the meaning. So